Okay, let's unpack this. Have you ever stopped to truly appreciate the unsung hero of every building, the silent guardian standing watch above our heads? It's something we encounter every single day on every structure, yet, well, we rarely give it a second thought. Today, we're taking a deep dive into the fascinating, intricate world of roof systems.
It really is fascinating. And a roof is profoundly more than just a simple cover. It's really a highly engineered, complex system, a critical component of any building's performance. And it's designed to achieve so much more than merely keeping the rain out. We often perceive it as just like a protective lid, but its multifaceted functions extend way beyond that basic role.
Absolutely. And for this deep dive, we pulled together a rich collection of insights, specific terminology, and detailed structural elements about roofs. Really comprehensive stuff. We'll explore everything from their fundamental life-sustaining functions to their myriad forms and the intricate engineering that makes them possible. Our mission today is basically to help you truly understand what's really going on up there, why every single choice in roof design and construction profoundly matters, and maybe reveal the incredible diversity in how buildings actually protect us from the elements.
Yeah, and by the end of this, you'll discover that the form and function of a roof are just so deeply intertwined. It's a delicate yet robust balance. You've got advanced engineering principles, cutting-edge material science, and even significant aesthetic considerations all playing together. This journey into the world above our heads will be, I think, a testament to human ingenuity in adapting to environmental challenges. You really will never look at a roof the same way again. You'll appreciate the silent, sophisticated work it does day in and day out. Get ready to have your perspective shifted, because you'll definitely be looking up at buildings with entirely new eyes after this.
So let's begin at the absolute core, because sometimes the most fundamental definitions hold the deepest insights, right? At its heart, the source material tells us the roof system functions as the primary sheltering element for the interior spaces of a building. Now, that sounds straightforward enough, but that single word, sheltering, is doing an immense amount of heavy lifting here, isn't it?
It undeniably is, yeah. When we speak of sheltering in the context of a roof, we're really talking about a highly complex, multifaceted protective system. Its primary role, the one most obvious to us, is naturally to shed elements. Think about the relentless assault of rainwater or, the persistent weight of melting snow. The form and slope of a roof aren't arbitrary design choices made purely for looks. Not at all. Instead, they must be meticulously compatible with the specific roofing material being used. For instance, a very low-sloped roof might rely on a continuous waterproof membrane like you see on commercial buildings, whereas a steeper pitch is ideal for individual shingles or tiles, basically allowing gravity to do most of the heavy lifting.
Okay, so it's not just about what hits the roof, but how it's then actively managed and directed away from the building. That makes sense?
Precisely. This shedding process is seamlessly integrated with a whole sophisticated network of drains, gutters, and downspouts. These components aren't just tacked on at the end, they're an essential part of the overall system. They have to work in perfect concert to efficiently channel water away from the building's critical foundation and walls. Without this effective diversion, water can pool, it can accumulate, leading to erosion, foundation damage, and even compromise structural integrity over time. It's a continuous kind of invisible dance of deflection and drainage happening up there.
That's a lot more involved than just a simple rain shield.
Yeah.
And it goes beyond just water, doesn't it? What about things we can't see, like moisture in the air or heat?
You've hit on a really critical point there. Beyond just shedding physical precipitation, the roof system plays an absolutely crucial, often unseen role in controlling environmental passage. This encompasses several key elements that directly impact a building's interior environment and, crucially, its energy efficiency. For instance, it's designed to precisely control the passage of moisture vapor. This is huge. Without proper vapor control, which involves the strategic placement of vapor retarders or barriers within the roof assembly, condensation can silently build up inside the unseen roof structure itself. This internal moisture can lead to really insidious problems like mold growth, rotten wood components, and long-term material degradation, all without you ever seeing a single drip inside the living space.
Wow, so it's not just stopping liquid water getting in, but managing humidity at a microscopic level within the structure itself.
Exactly. And beyond moisture, the roof acts as a critical barrier to control the infiltration of air. Now, this isn't just about preventing a draft, feeling a bit chilly. Uncontrolled air leakage allows conditioned air, the air you've paid to heat or cool, to escape in winter, and unconditioned outside air to enter in summer. This directly impacts your indoor comfort and significantly drives up energy consumption for heating and cooling. It's a major factor. So, a well-designed roof system integrates air barriers that create a continuous sealed envelope working with the walls. And speaking of energy efficiency, the roof is absolutely vital in managing the flow of heat and solar radiation. Its material choices, the color, the insulation levels, these determine how much heat penetrates in hot climates, requiring more air conditioning, or how much heat escapes in cold climates, demanding more heating fuel. High-performance insulation, maybe reflective coatings on roofing materials, even strategically placed radiant barriers can drastically reduce a building's energy footprint. This really makes the roof a cornerstone of sustainable design, something we're thinking about more and more.
That's an incredible amount of work for something we usually just look past. Just amazing. And then there's the safety aspect too, which honestly is something I rarely consider from the perspective of a roof.
Indeed. And it's vital. Depending on the type of construction, the building's occupancy, is it a house, a school, an office, and the local building codes. The roof structure and its entire assembly may also be mandated to resist the spread of fire. This is a paramount safety function. A roof with a high fire resistance rating acts as a critical compartmentalization element. It helps to contain a fire within a specific area and slow its progression throughout the building. This is literally life-saving. It provides invaluable time for occupants to evacuate safely and for firefighters to respond effectively. It can often prevent total structural collapse and, well, save lives. And this isn't just about the surface materials you see, like shingles. It extends deep into the very structural components and the layers of the roof assembly itself. Different materials and assemblies are rigorously tested and rated for fire endurance. You might hear terms like Class A, B, or C. Class A offers the highest resistance, which is obviously crucial for public and commercial buildings.
Okay, so really, the roof is this comprehensive, multi-layered barrier, almost like the sophisticated lid of a sealed container, protecting everything inside from a whole multitude of threats.
That's a perfect analogy, yeah. It's absolutely essential to understand that the roof is not an isolated component just sitting on top. It's an integral, indispensable part of the overall building envelope. This envelope is the complete physical separator between the interior, conditioned environment of a building and the harsh, unpredictable exterior world. As its uppermost segment, the roof provides comprehensive protection from a multitude of external factors. It keeps out animals, birds, squirrels, you name it. It defends against all types of weather, notably rain, as we've discussed, but also the erosive power of wind, the damaging effects of intense heat, and the degrading impact of direct sunlight, UV radiation. It truly is the building's primary line of defense, a meticulously designed shield against the outside world.
And it's not just the protective layer on top that we see, is it? It's also the very bones, the underlying structure that holds that layer up, giving it its form and its strength.
That is a crucial distinction, yes, and it often leads to a common misunderstanding. There's a fundamental duality to the roof system. On one hand, you have the visible covering material, the shingles, the tiles, the metal panels, or the membrane, which provides the primary weather barrier. That's what we see. But equally important, and often completely unseen from the ground, is the framing or structure that supports that covering. This underlying skeleton is what gives the roof its specific form, its incredible strength, and its ability to withstand various loads. And these loads include not just the weight of the roofing materials themselves, what engineers call the dead load, but also dynamic forces like the weight of snow, which can be immense, the tremendous uplift and lateral pressures from wind, and even occasional live loads from, say, maintenance workers walking on it. Understanding this duality, the covering and the structure, is absolutely vital for grasping how a roof is actually built and how it performs all its complex functions.
Now, here's where it gets really interesting for anyone wanting to truly understand these amazing structures. Because just like any specialized field, medicine, aeronautics, roofs have their own unique, precise language. If you've ever heard builders, architects, or even home inspectors talking about a building, they often throw around terms that might sound like a secret code. Understanding these specific terms doesn't just help us appreciate the precision involved in their design and construction, it also just makes you incredibly informed when you're looking at buildings or, heaven forbid, dealing with a roof issue.
That's so true. This specific vocabulary is absolutely essential for clear communication and precise execution, both in the design phase and definitely during construction. Let's meticulously break down some of these essential terms, try and paint a clear picture for you. First up, we have the ridge, RIDGE. This is the horizontal line of intersection that you find at the very top. where two opposing sloping planes of a roof gracefully meet. You can literally think of it as the apex, the crowning line, or the highest linear point of a traditional pitched roof, like the spine. It's not just a visual marker, it's a key structural element. It often defines the overall length and orientation of the roof itself. And it's commonly where you'd find a ridge vent, which is crucial for attic ventilation.
Okay, so it's essentially the very peak, the backbone line running along the top of the house. Got it.
Exactly. Now, moving on, we encounter a hip, HIP. A hip is the inclined projecting angle formed by the junction of two adjacent sloping sides of a roof. Unlike a ridge, which runs horizontally, a hip slants downwards from the ridge, or sometimes from a common high point, down towards the eave line. Imagine a roof where all four sides slope inward towards the center, like a pyramid shape, but elongated maybe. That creates hips at the diagonal junctions. They form a distinct visual and structural element, often seen on roofs that create a very clean, continuous look around the building's perimeter. And interestingly, hip roofs are known for their excellent wind resistance because those sloped ends deflect wind currents more effectively than sharp vertical gable ends.
Ah, okay, so hips are the outward sloping corners. And where two roof surfaces meet inwards, that's something different, right? A point where water tends to collect.
You're thinking of a valley. Valley, yes. A valley is an intersection where two inclined or sloping roof surfaces meet to form an internal angle, like an inward fold. Picture two wings of a house coming together at an L shape, and where their roofs converge, that's precisely where you'll find a valley. Because they naturally collect and channel large volumes of rainwater and melting snow, proper design and meticulous waterproofing, often involving specialized metal flashing in valleys, are absolutely critical. Non-negotiable, really. A poorly designed or inadequately sealed valley is, unfortunately, one of the most common culprits for persistent roof leaks. It makes it a high-risk, high-importance area for builders.
I can certainly see why that would be a high-stakes area. It definitely needs to be done right. What about the flat, triangular part of a wall that you often see on the end of a house, connecting directly to the roof slope?
That distinctive triangular section is called a gable. Gable. A gable is the triangular portion of a wall that completely encloses the end of a pitched roof, extending from the ridge all the way down to the eaves line. It is arguably one of the most common and instantly recognizable features of residential architecture, effectively defining the classic house shape that, children often draw. Its commonality also provides a wonderful canvas for aesthetic variation. It influences the placement of windows, the choice of siding, trim details, and the overall architectural character.
Right, the classic house shape. And those charming little structures that seem to pop right out of the main roof slope, often with their own windows, they have a specific name, don't they?
Indeed, those are dormers. Dormers. Dormers are projecting structures built directly out from a sloping roof, and they typically house a vertical window or sometimes a ventilating louver instead of a window. They serve a really neat dual purpose. Functionally, they bring much-needed natural light and ventilation into attic spaces. They can transform otherwise dark and unusable areas into livable rooms, like bedrooms or offices. And aesthetically, they add significant visual interest, breaking up the monotony of a large roof plane and contributing hugely to the architectural style and charm of a building. They can range from very simple, understated designs like a shed dormer to quite elaborate and decorative elements like gabled or eyebrow dormers.
Okay, dormers, got it. Now, what about the edges of the roof? We have the part that hangs over horizontally, the eave, but there's another term for the sloping edge on the gable end, isn't there? The angled edge.
That would be the rake, R-A-K-E. The rake is the inclined, typically projecting edge of a roof that runs along the gable end, rather than horizontally along the eave. It essentially follows the slope of the roof up from the eave to the ridge on that triangular gable wall. It's often finished with a trim board or fascia, much like an eave, but its inclined nature makes it distinct. Differentiating the rake from the eave is important because the rake deals with the vertical termination of the roof plane on a gable end, whereas the eave is the horizontal overhang along the length of the wall.
Okay, so rake is the edge on the triangular gable part. And then a very simple roof form also has its own specific name, right? For something like a lean-to or an addition.
Yes, that's precisely a shed roof, S-H-E-D. A shed roof is simply a roof having a single continuous slope, just one plane. It's one of the most basic, straightforward, and practical roof forms. You often see it employed for utilitarian structures like, sheds or lean-tos attached to a main building, or sometimes as part of modern, minimalist architectural designs where that clean, single slope is desired. Its inherent simplicity makes it relatively economical to build and provides for very easy water drainage in just one direction.
Simple and effective. And the part that hangs over the walls, protecting them from rain, we mentioned it briefly.
That's the eave. E-A-V-E. The eave is the overhanging lower edge of a roof that extends beyond the face of the exterior wall below it. Its primary function is actually multifaceted. First, it actively protects the walls and foundation of the building from the direct impact of rainwater runoff, helping to prevent moisture intrusion and splashback damage at the base of the wall. It also provides essential shade from direct sunlight, particularly high summer sun, which reduces solar heat gain on the walls and windows, helping keep the interior cooler. And aesthetically, it contributes significantly to the overall proportion and character of a building. The size of the overhang can really change the look.
Right, the overhang. And underneath that eave, there's usually a finished surface, right? It's not just open framing under there.
Correct. That finished surface underneath the eave is known as the soffit. S-O-F-F-I-T. The soffit is typically finished with materials like plywood, fiber cement board, vinyl, or aluminum, providing a clean, protected underside to the overhanging roof eave structure. Its purpose is to protect the structural components of the eave, the rafter tails or truss ends, from weather exposure, nesting pests, and sometimes even fire spread. Crucially, the soffit often contains strategically placed vents. You'll see little grills or perforations. These allow for proper attic ventilation. They work in conjunction with ridge vents or gable vents to ensure air circulates through the attic space. This prevents damaging heat buildup in summer and moisture accumulation in winter. Proper ventilation is vital for the longevity of the roof system itself and for the energy efficiency of the whole building. So together, these terms ridge, hip, valley, gable, dormer, rake, shed, eave, soffit form the absolutely essential language for describing the components of virtually any roof. Knowing them allows for precise discussion, design, and execution.
It's truly incredible how specific each part is, and how these terms are the fundamental building blocks for describing all the different roof forms we see every day. Knowing these definitions really does unlock a deeper, more nuanced understanding of how a roof is conceived, constructed, and ultimately how it performs its vital functions. It's like learning a new language for buildings.
And if we connect this to the bigger picture, the choice of a building's roof system, meaning the underlying structure, is not just an aesthetic decision, not by a long shot. It profoundly dictates the entire building's structural approach, its capabilities, and its long-term performance. The materials and construction methods chosen for the primary structure of the roof are absolutely fundamental to the building's overall stability, its ability to span large distances, and its resilience against environmental forces like wind and snow. It's the skeleton, really, that provides the strength for the skin we see.
Okay, so it's not just about the outer skin, the shingles or metal. It's about the very skeletal system that gives the roof its enduring strength and form. What are some of these foundational structural systems that architects and engineers rely on, especially for different types of buildings?
Well, one of the most robust and enduring options, particularly for larger or more demanding structures, is the reinforced concrete roof slab. This is a monolithic system. Think solid, incredibly heavy, yet immensely strong. Liquid concrete is poured directly over a meticulously arranged grid of steel reinforcing bars, or rebar, to create a continuous, solid slab. It's extensively used in commercial buildings, especially for flat or low-slope roofs, which are common in commercial construction. And it's particularly prevalent in regions that demand extreme durability, like areas prone to hurricanes or seismic activity, given its inherent resistance to high winds, impacts, and tremors. The advantages are numerous: exceptional durability and longevity, first off. Then there's inherent fire resistance because concrete is non-combustible. And significant thermal mass. This thermal mass is where the aha moment often comes in for people. Its sheer bulk means it absorbs and releases heat very slowly, acting like a giant thermal battery. This significantly stabilizes indoor temperatures, reducing the load on a building's heating and cooling systems, especially in climates with wide day-to-night temperature swings. However, its immense weight is a big factor. It necessitates a very strong supporting structure below strong columns, strong walls, strong foundations. And it requires careful detailing during construction to prevent cracking and ensure effective, long-lasting waterproofing, because even concrete isn't inherently waterproof over time without protection.
That makes perfect sense for large, sturdy buildings, where stability and fire resistance are absolutely paramount. But what about structures that need more flexibility, maybe lighter construction, or really vast open spaces without internal supports like columns?
For those applications, structural steel roof framing is an incredibly versatile and immensely strong alternative. Steel allows for a great deal of design flexibility and can span much larger distances than traditional wood framing, making it ideal for those large-span, open-plan buildings. Within structural steel, we primarily utilize a couple of key approaches. One is steel rigid frames. Now, a rigid frame is a sophisticated structural system where the beams and columns are not simply pinned together like hinges. Instead, they are connected in such a way that they resist bending moments, creating a very stiff and strong overall framework. These are called moment-resisting connections. It means the joints themselves can transfer bending forces efficiently throughout the structure. This essentially makes the columns and beams act as one continuous integrated unit. The significant advantage here is that rigid frames allow for truly large, clear spans without the need for interior columns, huge open spaces. This makes them ideal for spaces that require wide open areas, such as expansive warehouses, manufacturing facilities, aircraft hangars, convention centers, or large sports arenas where any internal obstructions would be completely undesirable.
Right. So that's how they achieve those huge, unobstructed spaces we see in modern stadiums and exhibition halls. Clever engineering at the connections. What's the other main type of steel framing you mentioned?
The other key type, really renowned for its efficiency, is steel trusses. Trusses are structural frameworks composed of individual members, typically steel angles, channels, or tubes connected at their joints or nodes, to form a series of triangular units. The reason triangles are used is absolutely fundamental to their incredible strength and efficiency. Triangles are inherently stable geometric shapes. Unlike rectangles, which can easily deform into a parallelogram under load if the corners aren't rigid, triangles cannot change shape without the actual length of their sides changing. This makes them incredibly rigid and exceptionally efficient at distributing loads. They channel forces primarily as pure tension, pulling apart, or compression, pushing together, along their members rather than complex bending.
Ah, the genius of the triangle. So it's distributing forces through simple pushes and pulls rather than making the members bend, which is much harder for them to resist.
Exactly. Pure tension and compression are much more efficient ways for materials to handle load. This allows engineers to span massive distances using surprisingly little material, making trusses very weight efficient and often cost effective. Now, there are many specific types of trusses designed for different spans, load conditions, and architectural requirements. Each has specific configurations of top chords, the top members, bottom chords, the bottom members, and web members, the diagonals and verticals in between. For instance, a simple king post truss is often used for shorter spans, while more complex Pratt or Howe trusses are common for longer spans, each with distinct diagonal arrangements optimized for different load patterns. The source material also mentions building and installing metal roof trusses, which highlights a key aspect. These are often prefabricated off-site with incredible precision engineering in a controlled factory environment. They are then transported to the site and lifted into place, which significantly speeds up construction time on site and ensures higher quality control compared to building them piece by piece in the field.
So trusses are all about creating strong, lightweight structures through clever geometry and efficient, often off-site fabrication. That makes a lot of sense. What about the material that goes on top of these robust steel frames? The trusses or the rigid frames to create the actual roof surface before the final waterproofing.
Right, you need something to stand between those main structural elements. That's where metal roof decking comes in. This is typically a corrugated metal sheet, often made of galvanized steel or sometimes aluminum. Corrugated means it has folds or waves in it, like cardboard. It spans between the roof joists, smaller beams, or purlins. Those are the horizontal supporting members attached to the main trusses or frames. Its primary function is multi-layered. First, it provides a strong, rigid base for the subsequent layers, the insulation, and the final roofing membrane, whether that's a built-up asphalt roof, a single-ply TPO or EPDM membrane, or another system. Second, that corrugated profile gives it immense strength relative to its weight. It's surprisingly strong. And third, it often acts as a structural diaphragm. That means it helps resist lateral forces like wind or seismic loads by tying the entire roof structure together horizontally, making the whole system stiffer and more stable. The advantages of metal roof decking are pretty significant. It's lightweight, which reduces the load on the supporting structure and foundations. That's a big plus. It has a high strength to weight ratio, meaning it's very strong for its relatively light mass, efficient use of material, and it allows for incredibly fast installation. Large sheets can be quickly laid down and fastened, greatly accelerating the construction schedule, which saves time and money.
Okay, so it's the corrugated sheets that form the base. It's amazing how each component, from the super heavy concrete slab to the relatively light metal decking, has such a specific and vital role in creating the complete roof system depending on the building's needs.
Absolutely. It's all about choosing the right system for the job balancing cost, performance, longevity, and structural requirements.
So we've talked structure. What does all this structural possibility mean for how buildings actually look and perform aesthetically and functionally? The forms a roof can take are just incredibly diverse, aren't they? Driven by everything from the local climate conditions it needs to withstand, like heavy snow or high winds, to deep cultural aesthetics, historical influences, and even just the available building materials in a region. These shapes aren't just decorative flourishes, they seem profoundly functional and often tell a story about the building and its environment.
Absolutely, you've nailed it. Let's really dive into some of the specific forms, because this is where the character and often the sheer ingenuity of a building truly starts to shine through. We'll cover an extensive range listed in our source material, each with its unique story and purpose. It's quite a list.
Let's do it. Starting with the absolute simplest one we already touched on.
Certainly. We begin again with the shed or lean-to roof. As we discussed, this roof has just a single continuous slope, like a ramp. Its profound simplicity makes it incredibly economical to build and provides for very straightforward water drainage in one direction. No complex valleys or hips. You'll often see it on utilitarian structures, simple additions, porches, or in modern minimalist designs where those clean lines and functional efficiency are paramount. Moving to perhaps the most common, we have the ubiquitous gable or pitch roof. This is characterized by two sloping sides that meet gracefully at a central ridge, creating those distinctive triangular ends, the gables we talked about. It's arguably the most prevalent residential roof form in temperate climates globally. Why? Because of its simplicity, ease of construction, and exceptional effectiveness at shedding both water and snow. Plus, it provides ample attic space for storage or conversion and allows for a wide variety of architectural expressions through the gable ends.
That's the iconic one we drew as kids when illustrating a house, right? The triangle top.
Precisely. Can't get more classic than that. Then, for a completely different function, consider the sawtooth roof. This is a fascinating form. Imagine a series of parallel gable roofs lined up, but with one side of each gable being much steeper than the other, and often incorporating vertical sections that contain windows, usually facing north in the northern hemisphere. This creates a distinctive saw-like profile when viewed from the side. It was historically, and still is sometimes, primarily used in industrial buildings and factories. Why? To maximize natural daylight deep inside the building, those vertical windows let in lots of diffuse, indirect light without the harsh glare or heat gain of direct sun, which was crucial in pre-electric lighting eras for illuminating large factory floors. It's a purely functional, yet visually striking architectural form.
Wow, so it's like a repeating pattern of small roofs, specifically designed for light and air, not just shedding water. Very cool.
Exactly. Form following function very directly there. And then there's the double gable, which, as the name pretty much suggests, is an extension or a more complex combination of gable roofs. This form is often used to accommodate an L-shaped or T-shaped floor plan, or maybe to signify different wings or additions to a building. It adds architectural interest and complexity compared to a simple gable, and can effectively define distinct sections of a building's layout while maintaining that familiar gable aesthetic. Next, we have the classic hip roof, which we also touched on with the term hip. Unlike a gable roof where two sides slope and two ends are vertical, the gables, all sides of a hip roof slope downward from a central ridge or point to the walls. Typically, there are no vertical gable ends. This creates a very stable roof structure, particularly resistant to wind uplift, as we mentioned. That's why it's a popular choice in hurricane-prone regions or areas with high winds. Aesthetically, it often contributes to a more traditional, grounded, and substantial look for a building, with a continuous, often elegant eave line all the way around.
Yeah, I can certainly visualize how that continuous slope all around would be incredibly beneficial in strong winds, offering less flat surface for the wind to push against or lift.
Indeed. Wind dynamics are a big factor there. A natural progression from that, especially on more complex house shapes, is the hip and valley roof. This is a very common and often quite intricate combination of hip and valley elements. You'll frequently see this on buildings with more complex or irregular floor plans, maybe multiple wings, extensions, garages attached at angles. It requires the seamless integration of both the outward-sloping hip sections and the inward-sloping critical drainage points of the valleys. This demands meticulous design and a very careful construction to ensure proper water management across its complex geometry. Lots of potential leak points if not done right.
Makes sense. More corners, more complexity. And what about those striking, pure pyramid-shaped ones we sometimes see on smaller, often decorative structures, like on top of a gazebo?
That's a pyramid roof. Pretty self-explanatory name. It's characterized by 4 triangular sides that all ascend and meet precisely at a single point at the very top, forming a perfect pyramid shape. You'll often see this form capping smaller structures like gatehouses, pavilions, gazebos, clock towers, or even certain types of towers and turrets on larger buildings. It creates a very distinct, often formal, and compact silhouette. It offers both structural stability due to its geometry and a strong visual statement.
Okay, simple but striking.
Oh.
Now, what about the kind of roof you often associate with old barns? The ones with two distinct slopes on each side, where the lower one is much steeper on just like a broken slope.
You're perfectly describing a gambrel roof. Gambrel. This is a symmetrical, two-sided roof, but the key is it has two different slopes on each side. The crucial feature is that the lower slope is typically much steeper than the upper one, which is shallower. This design is absolutely iconic for barns, giving them their characteristic profile. Why? Because that steeper lower slope maximizes the usable headroom and floor space within the attic or loft area. This made it ideal historically for storing huge amounts of hay or creating workshops or even providing extra living space up there. It's a very practical space-maximizing design that combines efficiency with a kind of rustic, traditional aesthetic.
That's so clever.
Yeah.
It really changes the usable volume under the roof just by changing the pitch partway down.
Yeah.
Genius. What about something perhaps more purely decorative, almost whimsical, with curves?
For something more decorative and flowing, featuring curves, there's the ogee roof, O-G-E-E. This roof is characterized by an elegant S-shaped curve in its profile. Typically, it's concave, curving inwards near the bottom edge, and convex, curving outwards towards the top. It's often found in traditional, ornate, or even exotic architectural styles. You might see it capping certain types of towers, cupolas, or influenced by designs like pagodas or some historical domes. It adds a very distinctive, curvilinear, and often highly elegant element to a building, providing a sense of fluidity and perhaps historical grandeur or fantasy. Not very common, but very noticeable.
S-curve roof, okay. And the one that effectively creates entire extra floor within the roofline, often with those rows of windows poking out, giving a sense of Parisian charm. We see those a lot in cities.
You've nailed it. That's the mansard roof. M-A-N-S-A-R-D. Named after the French architect François Mansart. This is a sophisticated four-sided hip roof, essentially, but like the gambrel, it has two distinct slopes on each of its sides. The critical distinction is that the lower slope of a mansard is much steeper than the upper slope, often almost vertical, and it's typically punctuated with those distinctive dormer windows we talked about earlier. This ingenious design, which really took off in 17th century France, was a brilliant architectural hack, essentially. It allowed buildings to effectively expand upwards by creating an entire usable floor, often called a garret or attic story, right within the roofline itself. This could double a building's functional space without officially adding another story in the traditional sense. Sometimes this was even done to get around property taxes that were based on the number of full stories below the roof. Aesthetically, it adds a grand, elegant, and often very European look. And our source also notes the French, or concave mansard, which is a delightful variation, perhaps featuring a more pronounced inward curve on that steep lower slope, adding an even more refined or specific architectural detail.
I love how those roofs just seem to magically create more space and impart a completely different character to the building. Fascinating history, too. What about roofs specifically designed for tall, narrow structures, like towers or turrets?
For towers or turrets, or anything with a circular or polygonal base that needs to go high, you'll often encounter a conical roof or spire. As the name suggests, this is a cone-shaped roof, typically rising to a sharp, slender point. It's a classic architectural element for features that need to emphasize height. It provides both a striking visual cap to a circular or pointed footprint and an exceptionally efficient way to shed water and snow off a tall structure. From fairy tale castles to church steeples to missile nose cones, these roofs evoke a sense of height, aspiration, and sometimes defense.
Point taken. And one of the most globally recognized, truly iconic roof forms seen on monumental architecture throughout history. Grand buildings often have these.
Of course, that would have to be the dome. D-O-M-E. This is a majestic hemispherical or sometimes slightly pointed vaulted roof structure, essentially forming a partial sphere or spheroid. Domes are absolutely iconic in monumental architecture, stretching back thousands of years. Think of the ancient Roman Pantheon, grand cathedrals like St. Peter's Basilica, mosques, capitol buildings, modern stadiums, and observatories. They symbolize strength, unity, the heavens, and often civic or religious grandeur. Structurally, they are incredible feats, capable of covering vast open spaces without the need for internal columns or supports. Their engineering is a marvel, as they distribute the immense weight downwards through complex compressive forces acting within curved rings.
Truly awe-inspiring structures. And then something completely completely different, almost like an inverted gable with a distinctly modern, maybe even mid-century aesthetic.
That's the butterfly roof, an evocative name. This is essentially an inverted gable roof. Instead of two planes sloping upwards to a central ridge, the two roof planes slope downwards towards a central valley or gutter running down the middle. It creates a distinctive V shape resembling butterfly wings outstretched. This design is often chosen for its unique, dynamic, and distinctly modern aesthetic. It became popular in mid-century modern architecture. Functionally, it can be very practical for rainwater collection in arid regions, as all the water is naturally directed towards that central channel for harvesting or controlled drainage. It also allows for higher exterior walls at the outer edges compared to a traditional gable, which can be advantageous for incorporating large, clerestory windows for natural light and views while maintaining privacy.
Butterfly roof, got it. It's truly amazing how each shape serves such a distinct purpose or set of purposes. Whether it's efficiently shedding snow in cold climates, catching natural light deep inside a factory, maximizing interior space like the gambrel or mansard, resisting high winds like the hip roof, or simply creating a powerful architectural statement like a dome or a spire. The diversity is absolutely astounding when you start to really look at them with an informed eye. It really is, and this naturally raises that incredibly important question again. How are all these incredible shapes, from the simplest single-sloped shed to the most complex dome or hip and valley combination, actually supported? What holds them up? That brings us back to the fundamental framing systems that give a roof its underlying structure, its stability, and its ability to perform its function over decades. The form is what you see, the aesthetics, the character, but the framing is the essential backbone, the often unseen muscle and bone of the roof.
Right. What's the most common type of framing we see, especially in residential homes in many parts of the world? The traditional method. That would overwhelmingly be rafter-type framing, specifically what's often called stick-built construction. This system uses individual sloping structural members, usually solid wood lumber, known as rafters. These extend from a ridge board or ridge beam at the peak, or sometimes from a central meeting point, down to the top plate of the exterior walls at the eave line. They are meticulously cut to precise lengths and angles, traditionally right on the job site, to create the desired roof pitch and overall form. Rafter framing is incredibly common in residential construction, particularly for custom homes or complex designs, because it offers immense flexibility. You can create almost any shape. It's great for accommodating complex roof lines with hips, valleys, and dormers, and for creating usable attic spaces or dramatic vaulted or cathedral ceilings below, because there isn't necessarily a horizontal tie across the bottom like in a truss.
Okay, so it's essentially building the roof slope piece by piece with individual angled beams cut and fitted on site. What are some of the nuances or variations within rafter framing?
Well, within rafter framing, there are very specific types and configurations the source mentions, types of rafter framing as a category. You have your basic common rafters that run straight from the ridge down to the eave, forming the main slope. But if you have a hip roof or valleys, you also need hip rafters running down the hip line, valley rafters running down the valley line, and various shorter jack rafters, common hip or valley jacks, that connect from the wall plate up to these hip or valley rafters at an angle. The engineering complexities involve calculating all the correct lengths and angles, especially the compound angles for hip and valley jacks, which used to require complex geometry or specialized framing squares. And critically, ensuring that the outward thrust generated by the sloped rafters they want to push the walls outwards is properly resisted. This is often done using the ceiling joists of the floor below, which span between the walls and act as rafter ties, holding the bottoms of opposing rafters together. Or in some designs, a structural ridge beam is used at the peak, which carries the vertical load and eliminates the outward thrust, allowing for open vaulted ceilings. It's a very adaptable, hands-on, traditional approach, though increasingly, pre-cut rafter packages or panelized systems are used to increase efficiency and precision even within stick framing.
Fascinating. So much geometry involved. What about more modern construction methods that might use different materials, perhaps lighter but equally strong, or offer other advantages?
Yes, absolutely. For more contemporary projects and often for larger scale commercial or multifamily residential buildings, or where efficiency, non-combustibility, or pest resistance are critical, we increasingly see light gauge roof framing, sometimes called cold-formed steel framing. This method utilizes thin engineered steel members. Now, these aren't the heavy, hot-rolled steel I-beams you'd associate with skyscrapers or bridges. Rather, they are precisely engineered channels, studs, like wall studs but for roofs, and tracks formed from thin sheets of galvanized steel that have been bent into specific C-shaped or Z-shaped profiles at room temperature, hence cold-formed.
Okay, so thin steel shaped for strength. What
Yeah.
are the compelling advantages of using this type of steel framing over, say, traditional wood rafters or trusses? Why choose this?
The advantages are quite compelling and really speak to modern construction demands and challenges. Firstly, light gauge steel allows for incredible precision in construction. The components are typically designed using specialized software and are often pre-cut and pre-punched for connections and fasteners in a factory setting. This minimizes cutting and waste on site and significantly reduces the chance of framing errors. Secondly, it offers significant material efficiency. Steel has a very high strength-to-weight ratio, meaning a lighter structure can still be incredibly strong and span considerable distances. This reduced weight can sometimes lead to direct savings further down the structure in the supporting walls, columns, and even the foundations, as they don't have to carry as much load. Furthermore, light gauge steel is inherently non-combustible, which offers superior fire resistance compared to wood. This is a major advantage for meeting stringent fire codes in certain building types or locations. It's also completely impervious to pests like termites and carpenter ants, and it won't warp, shrink, or rot due to moisture, which can be a major benefit for long-term durability, especially in humid or termite-prone regions. And crucially, as hinted at before, it's highly suitable for prefabrication. Entire roof panels or complex truss sections can be manufactured off-site under tightly controlled factory conditions, then simply shipped to the site ready for quick, precise assembly. This greatly speeds up construction time, reduces on-site labor needs, and can significantly improve overall quality control. It's really a testament to how modern construction pushes for smarter, faster, more efficient building practices, balancing strength, durability, and speed.
Wow, precision, fire resistance, pest resistance, speed. Quite a list of benefits. So whether it's the adaptable craftsmanship of traditional wood rafter framing or the modern efficiency and engineered precision of light gauge steel, the underlying structure of a roof is just as fascinating and absolutely critical as its outward appearance.
Absolutely. You got it. Each system, concrete slab, steel frame, steel truss, wood rafter, wood truss, light gauge steel, is carefully chosen based on a complex interplay of factors. You have to consider the building size and intended use, the local climate, snow loads, wind speeds, seismic conditions, budget constraints, the desired aesthetic outcome, and even the available skills and preferences of the local construction workforce. The framing is truly the unsung hero beneath the visible roof surface. It's doing all the heavy lifting, channeling immense loads safely through the building to the foundations, and allowing that beautiful exterior form, whatever it may be, to take shape while ensuring the building's long-term safety, performance, and durability against the elements.
So what does this all mean for us, the listeners, at the end of the day? We've journeyed from the fundamental, often overlooked purpose of a roof, that simple idea of shelter. We've delved into its intricate terminology, learning the language of ridges, valleys, eaves, and soffits. We explored the robust structural systems that hold it all together, from heavy concrete to intricate steel and wood framing. And finally, marveled at the sheer artistic and functional diversity of roof forms across the globe, from the simple shed to the majestic dome. It's been quite the ascent, revealing layers of complexity in something we maybe take for granted every single day.
It really has. And this deep dive truly highlights how something we often perceive as just a mere covering is actually a profound marvel of engineering and design working together. It is absolutely essential for our comfort, keeping us warm, dry, cool. It's essential for our safety, fire resistance, structural integrity, and indeed for defining the very character and style of our built environment. Every subtle slope, every strategic material choice, every hidden truss connection, and every intricate flashing detail is there for a precise reason, or usually multiple reasons. It's a testament, I think, to how deeply complex, thoughtful, and ingenious building construction truly is when done well. It encourages critical thinking, hopefully, about how seemingly disparate elements, things like material science, local climate patterns, human ingenuity, historical precedent, and even economic considerations, all converge to create such vital architectural elements that shape our world.
Absolutely. So as you go about your day, maybe on your commute tomorrow, walking down the street, or even just looking out your window, take a deliberate moment to look up. Really look. Now that you know the hidden complexities, the subtle angles, the robust engineering, the specific names for parts, and maybe some of the rich history behind them, how will you see the roofs around you differently? What surprising new forms or perhaps even functions might roofs take on in the next century, beyond just providing basic shelter? What's next for the roof?
That's a great question to ponder. Consider how escalating challenges like extreme weather events due to climate change, more intense rain, stronger winds, heavier snowfalls in some areas, Or the increasing global demand for sustainable and energy-efficient building solutions might push the evolution of roof systems even further, even faster. Will we see more roofs that actively generate significantly more energy than the building consumes? Roofs integrated with solar, not just as panels on top, but as the roofing material itself. Roofs designed to collect and purify vast amounts of rainwater for reuse within the building. Green roofs becoming standard not just for aesthetics, but for stormwater management and insulation. Maybe even roofs that can dynamically change their form or reflectivity in response to real-time weather conditions or energy needs. The roof isn't merely a static cap on a building, it is a dynamic, evolving, and critically important part of our architectural landscape, constantly adapting to new needs, new materials, and new innovations. There's still a lot happening up there.